We have already learnt about representing an organic molecule as molecular formula or branched formula or condensed formula. In this video, we will be learning another way of representing an organic molecule under structural formula, that is bond line formula or skeletal formula. This is the simplest way of expressing an organic molecule with its structure. This formula is also called as bond line representation or skeletal representation sometimes. In bond line formula, carbon atoms are represented by the vertices or dots. If we have 4 carbon atoms in the system, then it will be represented by 4 dots. If we have 5 carbon atoms, then it will be represented by 5 dots. Covalent bonds between carbon atoms are indicated by a line. If we have a single covalent bond between carbon atoms, then it is represented by 1 line. Double bond is represented by 2 lines. Triple bond is represented by 3 lines. Hydrogen atoms attached to carbon are implied in accordance with the octet rule. What does it mean? In skeletal formula, we don't write hydrogen atoms unless it is a part of functional group like aldehyde or carboxylic acid, or it is attached to a heteroatom like nitrogen, oxygen, sulfur. Number of hydrogen atoms on a particular carbon atom in skeletal formula will be understood or taken for granted based on the octet rule or valency of carbon. These points will become more clear when we consider examples. This is the branched formula for propane molecule, which is having 3 carbon atoms in it. As a first step to convert propane molecule into bond line formula, we have to write same number of dots as there are carbon atoms in propane molecule. We have 3 carbon atoms, so 3 dots. While writing the dots, we have to write them in a zigzag manner. If we write them in a linear manner, when we join them, we will not be able to identify how many dots are present. This is carbon number 1, carbon number 2, carbon number 3. In propane molecule, we have single bond between carbon atoms. So, we have to join dot 1 and dot 2 by a single line, dot 2 and dot 3 by a single line. This itself is the bond line formula or skeletal formula for propane molecule. How to read this? Observe. 3 dots indicates the presence of 3 carbon atom. On dot number 1, we have written 1 line. Since we know that carbon valency is 4, it is taken for granted that the remaining 3 lines are with hydrogen, or this carbon is attached to 3 hydrogen atoms. Going to dot 2, this carbon we have written 2 lines. Since valency of carbon is 4, we imagine that the remaining 2 bonds are with hydrogen, or in other words, this is CH2. In the same manner, dot number 3 or carbon 3 is having only 1 bond. So we imagine that the remaining 3 bonds are with hydrogen atom. In other words, carbon 3 is CH3. This is pentane molecule. Here we are having 5 carbon atoms. So we will have 5 dots in the skeletal formula. 1, 2, 3, 4 and 5. For the sake of clarity, let us number them 1, 2, 3, 4 and 5. Between the carbon atoms, we have single bond, so we need to join the dots by single lines. Since all other atoms are hydrogen in pentane, this itself will be the bond line representation for pentane. Prop 1ene has 3 carbon atoms in it, 1, 2 and 3. So there will be 3 dots in skeletal formula. 1, 2 and 3. We can see between carbon 1 and 2 we have a double bond. So we have to put 2 lines between carbon atom 1 and 2. There exists a single bond between carbon atom 2 and 3. So there will be a single line between 2 and 3. Rest are hydrogen atoms. Let us read this bond line representation. On carbon 1, we have written a double bond. So this carbon must be having 2 more bonds with hydrogen atom. That we can see here. Carbon atom 2, we have written 3 bonds on it. So there must be 1 more bond with hydrogen atom. See here. Carbon atom 3, we just have written 1 line. So there must be 3 more bonds with hydrogen atoms. We can see here. Similarly, let us do it for pent2ene, which is having 5 carbon atoms in it. So we will be writing 5 dots. One, 2, 3, 4 and 5. Between 1 and 2, we have a single bond. 3, 4, 5 also single bond. Between 1 and 2, single bond. 3 and 4, single bond. 4 and 5, single bond. Between 2 and 3, we have a double bond. So here we need to write 2 lines. Since rest is hydrogen, we can ignore it. This will be the bond line formula for pent2ene. In the cyclohexane structure, we have 6 carbon atoms connected in the form of a ring. Even in the skeletal representation, we will be writing 6 dots in the form of a ring. 1, 2, 3, 4, 5 and 6. Between the carbon atoms, we have single bonds, so we will be connecting the dots by a single line. This looks almost like a hexagon. Since rest of the atoms are hydrogen, we can ignore them. This is the bond line representation for cyclohexane. Coming to benzene, here also we are having 6 carbon atoms in the form of a ring. So we will be writing 6 dots in the form of a ring. For the sake of clarity, let us number the carbon atoms in benzene. We can see there exists a double bond between carbon 1 and 2, 3 and 4, 5 and 6. So we need to be writing 2 lines between 1 and 2, 3 and 4, and 5 and 6. There exists single bond between 2 and 3, 4 and 5, 6 and 1. So single line between 2 and 3, 4 and 5, 6 and 1. This is the bond line representation of benzene. This is the condensed formula of pentane 1-ol. There exist 5 carbon atoms in this molecule. So we will be writing 5 dots. Let us number them for the sake of clarity. There exists single bond between the carbon atoms, so we need to be joining these dots by a single line. Carbon atom 1 is connected to oxygen, that is further connected to hydrogen. We need not have to represent these hydrogen atoms because they are sitting on carbon atom. Since this hydrogen is sitting on the heteroatom oxygen, we should be representing this hydrogen atom even in the skeletal formula. Carbon atom 1 is connected to an oxygen atom that is further connected to hydrogen. So this is the bond line representation for pentane 1-ol. This is a complex molecule having many carbon atoms and heteroatoms connected in a complex manner. To write the skeletal formula of such a complex system, first find out the longest carbon chain, that is this in this system, and number them 1, 2, 3, 4, 5. Keep in mind, these numbers have nothing to do with IUPAC nomenclature numbering. First, let us convert these 5 carbon atoms into 5 dots in the skeletal formula. 1, 2, 3, 4, 5. We have single bond between these carbon atoms, so single line between the dots. For the sake of clarity, I will number these carbon atoms. We can see carbon atom 1 is connected to the functional group OH. Carbon atom 1 is connected to the functional group OH. We need to mention this hydrogen atom because it is connected to the heteroatom oxygen. Carbon atom 5 is connected to the heteroatom chlorine. That also we should represent. 5 connected to the heteroatom chlorine through a single bond. On carbon 3, we are having 2 carbon atoms connected through a single bond on one side. For the sake of clarity, I use the color code. 2 carbon atoms, meaning 2 dots, connected to 3 through a single bond. This carbon atom is further connected to oxygen through a double bond. So, double bond, oxygen. Though this hydrogen is sitting on carbon atom, we need to be showing this in skeletal formula because this is a part of the functional group aldehyde. So, hydrogen. On the other side, on carbon 3, we have an oxygen connected through a single bond. On this oxygen, we have 1 carbon atom connected through a single bond. So, 1 dot connected through a single bond. This is the skeletal formula for this molecule. This is the time to convert skeletal formula into condensed formula. Let us first identify the atoms and number of hydrogen atoms sitting on it. This is carbon. It is having only 1 bond in the skeletal formula. So there must be 3 more hydrogen atoms on it. So this is CH3. This carbon is having 2 bonds. So there must be 2 more hydrogen atoms. This is CH2. This carbon is having 3 bonds. So there must be 1 more hydrogen atom. So this is CH. This carbon with 1 bond, it will be CH3. This carbon is already having 4 bonds in the skeletal formula. So this is simply a carbon atom. Heteroatoms are anyway written. This carbon is also having 4 bonds. So no hydrogen atoms on it. It is a simple carbon. This carbon is connected with 2 bonds. So 2 more must be hydrogen atoms. This is CH2. For the same reason, this is also CH2. On nitrogen, we are having 1 hydrogen atom and 1 carbon atom. This carbon is having 1 bond. So remaining 3 must be hydrogen. So CH3. Condensed formula for this molecule will be CH3 connected to CH2 connected to CH This is connected to CH3 downwards. On the other side connected to carbon. That is connected to two oxygen atoms, one with a double bond, another one with a single bond. This is connected to another carbon, which is further connected to double bond O and to a CH2, another CH2, NH, CH3. In this cyclic structure, this carbon is having 3 bonds. So this is CH. This is also having 3 bonds. CH, CH. This is also CH. This is having 4 bonds. So C. This is also C. CH, C, CH, 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 C, CH. So condensed formula is CH, CH, double bond, CH, single bond, CH, double bond, C, single bond, C, double bond on one side, single bond on another side to CH, double bond C, single bond C, double bond CH. Here it is a single bond. This carbon is connected to another CH, double bond CH, single bond CH, double bond CH, and here we have a single bond. This molecule consists of nitrogen heteroatoms in it. Since the hydrogens sitting on heteroatoms are clearly shown in the skeletal formula, we just need to identify the carbons and the hydrogen sitting on it. This carbon is having 3 bonds, so there must be one more hydrogen. So this is CH. On this carbon, and this one, we are already having 4 bonds. So all these 3 are simple carbons. This carbon is having 3 bonds. So one more must be hydrogen. So this is CH. Condensed formula will be nitrogen connected to a CH, connected to NH, connected to carbon. This is double bonded to another carbon and there exists a single bond here. This carbon is connected to another carbon, that is to NH2. On the other side, it is double bonded to nitrogen, single bonded to CH, double bonded to nitrogen. Here there is a single bond.